saying that with Mark and with Dan that you are a very successful meeting because people is staying until very late. So we got, as organizer of this workshop, we have heard a lot of thanks and we are happy. But I just have to take advantage to revert these thanks to Michael Gill, to Valerio Lucarini, and all the other main organizers of this big umbrella event. And of course, we did that because Michael contacted initially Mark, Dan, myself to do these things. And so we start to put them together, the group. And so this is, you know, we did a little piece, we did a macro piece, which has been done by Michael primarily, and Valerio as well. Also, to take advantage of my slot of time to thank some of the founders that has founded this specific workshop. Michael already did that at the workshop, but part of the funding came from this workshop came from the ONR, which is the Navy Office of Research in the US, and I think we want to do that. And then this is my talk. So this is actually a talk I will use. Look at your. So this is a. I should not say that, as you can say before. These also are a bit of somehow old result. They are not aged, but they are. So this work originated actually by the work that a student, a master student of the École des Mines here in Paris, came to do an internship with me at the Nansen Center and with Stéphane Van Nitsem at RMI, and then he also interacted with Mark here in Paris. And then I have waited a bit too long to build up a paper based on that. So I decided to do it like finally this last summer. So this is about coupled data assimilation. Coupled data assimilation is, of course, the topic of what we have seen 2 talks ago. It has been in part what François Conillon spoke the first day, and this is probably the main thing that you can learn about coupled data assimilation. The challenge will be what you will see tomorrow by Philip Brown from the SNWF. So it is, in fact, I will say, primarily a technological challenge rather than a very conceptual new problem, because the challenge comes by the fact that the different compartments that we wanted to connect, they have a very spatial scale and spatial temporal scale which are separated. So here we wanted to elucidate some of the mechanism behind that. We will focus only on the case on system where the difference is in the temporal scale. So I will assume, and I will repeat that again and again, that they don't have a spatial scale difference, nor they have the different amplitude. So in general, of course, multi-scale arise in many areas of science. Typical when we continue system in high resolution, or when we're coupling together different. No, actually, it's not working. It's done. We consume the battery completely. So it's also when we couple together different subsystems, each one spanning its own band of scales. And of course, the classical example we have in mind comes by the climate model, which coupled together different components of the Earth system. So in this context, it is, the seasonal to decadal or subseasonal to seasonal forecast are exactly possible because there is this predictable signal which arises from the interaction that the atmosphere has with the slower component of the climate system. This is very well known, and it is also true that this S horizon is the one that has motivated this effort that has been done in many numerical weather / climate center to move toward this infrastructure they call seamless prediction, in which the same coupled model is used all the way through from the prediction of the 30 minutes all the way to the seasonal. So if we wanted to use this coupled infrastructure altogether, of course, then the problem is that if we wanted to combine them with data, is that we have to do this coupled data assimilation, which has been defined, I think, very well by Evnit before. So coupled data assimilation is needed because we wanted to enhance the predictive skill of phenomena, such as those, in fact, which are connected to the exchange between air and sea, or when we want to initialize a prediction, which need to be delivered by a coupled model, and this indeed is what people is doing at the Nansen Center, at the Birchen Center, and François was talking about that particularly. And this is also the reason why there have been many centers worldwide, SNWF is being one of them, which have been recently engaging a lot into developing coupled data assimilation. So the list of papers is very long. We have done our best to acknowledge all of them in the manuscript on which this talk is based. I only mention a few here. I mentioned this work by Steve Penn et al. Because, including this one with Thomas Emil, because it was a good picture of the state of the art, all the way from the statement of the problem to the state of the art in operational center, but also to play a bit the in-house game. I like to mention this work here, this is the reanalysis which is done at Nansen Center using a couple Oceanet and sea ice, and this reanalysis which is done using an ensemble Kalman filter. And actually, I think that this covered 30 here, but now they are I'm looking for François because maybe he knows more. He's part, of course, of this paper, but what I'm saying is that this is a paper in 2017. It covered 30 years, so it is available. You can use it, but now they are running it and they are extending it back in the past. So, of course, the main problem is that there is this scale separation, which makes it difficult to carry out the uncertainty quantification, which we need. So, essentially, to describe these forecasted covariance metrics in the proper way, because those are the way that the information will be moved from. So, usually, if the scale separation is not very large, one can still rely upon the classical uncoupled data assimilation, which means that you make the update separately in each model compartment, then you build up a common analysis and you use that analysis to run your forecast using a coupled model. So this is a way in which the coupling will manifest via the nonlinear via the nonlinear forward model. But of course, if you really wanted to transmit information at the level, at the moment when observations are collected, we need to do coupled data simulation, what we call fully coupled, or strongly coupled data simulation. In this talk, I won't use this distinction because I will only focus on strongly coupled data simulation, but it is very well known for people working in the domain that for weakly coupled, we intended a coupled model with a disjoint uncoupled analysis. For strongly coupled, it is when everything is together. So, in several papers, it has been clear that there was this influence on the atmosphere, on the ocean, and it has been also signalized by Avnit before using the lag, studying the autocorrelation. So we try to use some dynamical argument, and we find out actually the same. So the problem is we are dealing with this of this sort. So we have a coupled system, which is a prototypical of the possible ocean and the atmosphere. In this case, the ocean is because epsilon is taken to be smaller than 1. And then, of course, this is a coupled system, so this F function, this will represent the model of the ocean, the model of the atmosphere. They are connected together, so they are on this subspace, in this space of dimension x and z, and they are sent respectively in the space of the atmosphere and the ocean. So we are assuming here, as I said before, that F and G are both bounded from above as the order 1. This is just arbitrary, but what is matter here is that they are taking the same bound. And also I'm assuming that the characteristic spatial scale are the same. This is obviously not true as a remark here in realistic coupled system. But I need to make this hypothesis here because I wanted to only extract the effect, if any, of the temporal difference. So with this hypothesis, this means obviously that within a time interval, say, of order 1, the slow scale will change like this, while the fast scale will change like this. So, of course, the impact of the temporal scale will then affect the way how the scale will grow comparatively in the same interval. This is the model that we have, and we wanted to make data assimilation. So we assume that we have data in both now, in the ocean and in the atmosphere. Respectively, they can have different dimensions. Of course, it's very arbitrary. We assume also that the interval of the observation, so the observation frequency in the atmosphere is higher than in the ocean. In particular, I made the assumption here that the interval of the ocean observation is a multiple of that. This is not necessarily true, but this allows me to write the operator in this way. So it's very simple. So as soon as all time that when I have data in the ocean, I also have data in the atmosphere, but not vice versa. And I have observation in the atmosphere more often. This is nothing. So, of course, here I have to assume that the observation of the slow scale, we need to have the observation, the frequency of the observation in the ocean is bounded like this. Otherwise, I won't be able to monitor this variability. Now, obviously, if the interval of the observation in the ocean is order 0,1, then the solution in the fast scale is of order 1. The solution of the slow system is approximately constant in that interval. And this is the reason, when we are in this situation, of course, this is a good situation for the weakly coupled data assimilation. Or this is also a good situation to take an average of the fast scale subcomponent and observe only the average of the data, like it has been shown by Avneet before. So then I can linearize the error, and this is just these are not the Jacobian. These are the tangent linear model. Actually, these are the resolvent of the Jacobian. So by doing that, I can identify, for instance, the cross term. So sorry, the cross term. Here we see that the cross term will represent the effect of the fast to slow dynamic, which is given by this object here, and the slow to fast dynamic, which is given by this object here. Of course, these objects are given. We do not generally act on that when we do data assimilation. Unless you do parameter estimation, of course, but in the standard state estimation, you don't do that. And they, of course, encode all of the mechanical transfer, kinetic energy, and heat transfer that usually relate the atmosphere and the ocean. So I can take the order of this, and then I can take the norm of both sides, and I can have an equation like that. It's very simple. So then now I can have bounds. So this will tell me the order of the forecast error in the atmosphere, the order of the forecast error in the ocean. And this is bounded from above by this quantity here. So why this is useful? Well, this is useful because then I can use this equation, this inequality, and I can say, okay, suppose that I wanted to know how has to be how sensitive must be the ocean with respect to the atmosphere or vice versa, or the ocean with respect to the perturbation in the ocean, so that the forecast error in each component is kept to a given order. So suppose now that I hope that I have my forecast error of the same order of the analysis error of the previous time. It won't be the case, but not always, but this is at least what we can do by doing a good data assimilation, say. So in this case, I see that I can derive the two upper bound for first order upper bound for the slow scale and the fast scale, respectively, which are here. So this will represent, for instance, how is bounded from above the sensitivity of the slow scale over the slow scale. The slow scale over the slow scale over the fast scale, and so on and so forth. So this can tell me how big can be this sensitivity in order for the error in the forecast to be within the same scale of the error in the analysis. So of course, because of the temporal scale separation, what we see is that these bounds are bigger than this bound. And so the fast scale bounds are much smaller, so the analysis error must be kept within 0,1, otherwise locally large sensitivity beyond this will immediately lead to forecast error growth over the order of 1. So this is very much just a consequence of the temporal scale difference, and not all, and not more. There is nothing about the amplitude of the two quantity there. So if this is this is a very simple, it's a very simple linearized view, of course. They are not. But if I use that as to draw conclusion on how or where I should focus more on observing a coupled system. So the consequence that I picturize in this simple scheme here is that the cross-compartment effects are generally stronger in the direction from the slow to the fast scale. Okay. However, the inter-compartment effects are stronger in the fast scale, which is this, which require tasks to be controlled by the observation. So, I mean, the moral of this very simple linearized analysis is that you really want to control the fast scale here before then is moved down and contaminate the entire system. So it's this fast scale that must be observed primarily. So we have seen how this scenario reflected by doing simple experiment in a couple model. So the model that we use is the model that has been developed by Stefan van Nitsem and his group in the last years. So there are several papers that have appeared. The model is also available online. You can download it. It coupled together an atmosphere and an ocean, which are coupled together both mechanically and thermically. And the key, there are many things about this model which goes well beyond this talk, but the key things about this model is that its size can be arbitrarily changed. So the number of variables describing the ocean or the atmosphere can be changed accordingly. And we have worked here with 6 configurations, which are here, of different dimensions, respectively 36, 52, and 56. With 20, 16, 20, 32, 24, 32 respectively dimension in the atmosphere, in the ocean. And these three ensemble of configuration are characterized by different intense strength of the coupling. The first one are referred to as the weak couple. I'm not talking about the data assimilation. I'm talking about the strength of the couple between the ocean and the atmosphere in this model. So if you see like the long-term behavior of these, we say the attractor, because these are very, very long simulation for 10 to 7 days of this model. This is a representation in 3D on these 3 variables, which are the stream function, the second component of the stream function, and the temperature of the ocean, and the first stream function for the atmosphere. So this is the weak couple case and the strong couple case. So both, of course, are typical of typical attractor of a chaotic system. However, in this strong case, we can see that there is a shape which differentiates let's say, two sort of regime, two sort of period. A first period, which we call it the passive regime, which is characterized by low level of the stream function of the atmosphere. This is the time series of these, but on the variable of C1, and as opposed then to an area which we call the active regime, in which it is characterized by higher A value than of the stream function of the atmosphere and a higher variability. So these are how the physical correlation look like in Mahoma. This is not data simulation. I'm just running the model and computing the autocorrelation, spatial. So these are the instantaneous value, and then of course our average over many samples, but many interval. But this is the instantaneous, so you can clearly see that this is normalized with respect to so that the diagonal is 1. So you see that. Well, of course, you see that this is the part of the atmosphere, so the long-scale correlation that appear here. Then you see that the ocean, but what the point here is that you don't have much of cross-term here. Those are the cross-terms that you will need to have in order to transmit information across compartment. So when you do an average over a previous period of the data of the signal in the atmosphere, over 100 days or 1,000 days, then you see how we start to populate all this area here, which are in the cross term. This is as a motivation for performing the averaging of the data in the fast scale, or to use a lag method like the one that Avneet is studying. So these 6 configurations have been we also see how were the stability properties. These are collected in this table here. though when there are the number of positive, neutral, and negative Lyapunov exponent. Then we also computed the Kolmogorov entropy with a Kaplan-York dimension. We did that because we wanted ultimately to relate the performance of the data assimilation to this characteristic as well. This is the spectrum of Lyapunov exponent for the 6 configuration. And of course, the first things which is known about this model and have been also extensively studied by Stéphane before, and it is also, most of these, it is also collected in this paper that he did with Valerio in 2016, is the presence of many neutral modes. They are not all, of course, they are not all real neutral modes. Many of them are numerically seen as neutral, but they behave as such. So, and as I will show in the next slides, what is important is that this neutral mode seems to be very much connected to the mechanism of the coupling. And this is important for data assimilation. Well, I won't anticipate the conclusion, but so the fact that those modes are related or can be associated, particularly to the mechanism of the coupling, is a consequence of a plot like this. In this plot, we have the covariant Lyapunov vector. And of course, the computation of that is quite tricky. I must say that I should acknowledge Colin Grutzner because he helped a lot to compute this covariant Lyapunov vector when Maxime was doing that. And so here you have two configurations, a 36 variable weakly coupled and strongly coupled. These are the covariant Lyapunov vector. So you see they are 36 as a size, and these represent the projection, the average projection of each covariant Lyapunov vector along the state vector of the modes. So you clearly see that the CLV project largely on the atmospheric components, which are the first 20. And this is normal because this is where most of the instability is produced and is confined. Still, there is also in the state component related to the oceanic temperature significant projection, which are these parts here. And then the important, the point that I was making before is that the covariant Lyapunov vector which are associated to Lyapunov exponent close to 0, which is about this area here, they all display a significant projection on the oceanic string flow, which is this part here. And this is particularly true also for the strong case, of course. Obviously, all of these features are stronger in the case of the strongly coupled because who say something?
Sorry,
yeah.
Are we able to tell what the Lyapunov exponent is?
No, you cannot tell from this.
Okay.
You tell the Lyapunov exponent from the previous figure. Of course, I knew that. So there are very few positive Lyapunov exponents. So when I talk about CLV associated to the almost neutral one, I know that I have to move in this area here. The system possesses very few positive Lyapunov exponents, many almost 0, and a set of -1. So the point here is that this large projection connected to the neutral mode are very much, they seem to be very much a manifestation of the coupling. So now we run an ensemble Kalman filter. We decide to run a deterministic square root ensemble Kalman filter, and we did that because for previous work that we did, we believe that the connection between the stability of the system and the ensemble Kalman filter can be established only in the frame of square root ensemble Kalman filter. Among the many of them, we decided to work with the NKFN because we also have the possibility to avoid tuning on the inflation. So the inflation becomes an hyperparameter which is estimated along the flow. This is, of course, possible because the system is not that big. So this is the context. This is just a run of this with the observation everywhere. They are spatially uncorrelated, so the diagonal matrix, and this is the observational interval which is set to 24 hours in both systems. This is just to show that how the ensemble Kalman filter covariance look like. And this is the weakly coupled case. You see that essentially, if you do assimilation, most of the correction will be confined, respectively, in the ocean and in the atmosphere. Sorry, in the atmosphere and the ocean. There won't be much propagation. While when you move that from the weakly to the strongly coupled, of course, this seems that is the increased strength of the couple is manifested also in the ensemble Kalman filter error covariance, which now start to populate this area here. This is particularly so in the passive regime where most of the correlation is driven by the atmosphere. And so there is a communication between the two compartments. Now this is because you know that we like to this is our one of our main interests that we have had in the recent times, so to connect the performance of the filter and the function of the filter to the instability of the flow. So we just run a long experiment here by changing the number of ensemble members for the 6th configuration that I talked about, and so this is a root mean square error. This time is root mean square error also average in time, and you see that as we knew. And we have found already in uncoupled system in this work and in many other previous to that, even if in this one we really did for ensemble-based method, that you really need a number of ensemble member which is at least as big as the number of unstable and neutral modes, and which is indicated in the figure by the dashed vertical line there. Now, of course, there is a fact that there are many unstable neutral modes in this case, which makes the things a bit more complicated. So these are the experiment, and
so the error that you were showing is the error of the total system, the atmosphere, the ocean.
Yeah, it's the total system. Yeah, it normalized with adimensionalized with respect to each. So it's partially and timely average. And these are the experiment. This is just, there is no, you can just see what happened. It's nothing special here. You see that it is working very well. 15 member, the configuration is 36. This is the observational error, and in all cases, the analysis error, which is what I'm plotting together with the spread, the analysis error is below the observational error in both cases, and the spread is consistent with the analysis error. It's working well. Nothing particular. You can also check that. You can also see that the effect of the strong couple, which make the oscillation in the ocean much slower when the coupling is stronger than in the other case. Actually, the effect of the strength of the coupling is much more seen in the frequency of the atmosphere than in the ocean itself. Because in this case, the ocean is slowing the atmosphere. So this is the case when both atmosphere and ocean are both observed, and as a function of the observational interval, and it is worked very well. So this is the analysis error, and this is the observational error as a function of time. Fine. But then when I took the observation away from one compartment, so here I have observation only in the atmosphere, and here I have observation only in the ocean. So when I observe only in the atmosphere behaves very well. The ocean still behaves very well. So I can observe as often as 3 days, and still the ocean error will be below the observational error. And so, of course, then it will diverge. But there is an important part in which I'm able to control the ocean by only observing the atmosphere. When I do the opposite, so when I remove the observation in the ocean, when I remove the observation in the atmosphere, I only observe in the ocean error is still kept under control, even if it is not as good as in the previous slide when I was observing both compartments. But the error in the atmosphere jump and diverge to very high value, well above the observational errors. This is just a numerical proof of how important the observational in the atmosphere are in even this example. So the conclusion, I just packed it together. It's a bit to pack this. So we have deduced a very simple first-order dynamical mechanism for the error transmission. There are many other reasons that have explained the importance of the atmosphere. In the literature, you found much more arguments which are statistically based, I would say. The conclusion of that was that the cross-compartment effects are stronger in the direction from slow to fast, but the intercompartment effects are so strong in the fast scale that the fast scale need to be controlled before it affects the full system. We have confirmed this result in MAUAM. In this case, in MAUAM with NKFN, we also have seen that in the coupled system, there is a remaining chance of the uncoupled case in which we need to have a number of ensemble members which is bounded from below by N0, which N0 being the number of unstable and neutral modes. And of course, this is what, in a way, ultimately motivate our next step, which could be the one of trying to design reduced rank formulation on ensemble Kalman filter, a bit like what Colin did or suggested in this work. More generally, this map that we designed by the covariant Lyapunov vector and how they distribute the projection on the state index can be used to make target observation in a way, which is to indicate where a new sensor may be needed. Now, of course, we don't know how, and it will be interesting to see how this picture will change in the presence of spatial and amplitude difference as well. There is also one part that I want to do. This is a very slow model. So it's a model in which the ocean is basically not chaotic at all. We were discussing this with Stéphane yesterday, with Francois as well. And this is also one of the reasons why it is probably a good model if you wanted to look the long frequency variability in the long scale. But it's very special. So one of the things that we are considering is also to work with a model which has more, in more chaotic ocean. Okay, thank you. And this is the reanalysis paper of the, I say there are many more papers. There is also the reanalysis database in WF by Patrick Louraillot. So there are many other products that are now being delivered on coupled data simulation.
Thank you very much for your presentation, Alberto. In principle, we don't have any time for questions, but if you have pressing questions.
No, but I...
So, did you also look at all at coupling between the atmosphere or the troposphere and the stratosphere? Because I think you should, first of all, I think this is now kind of en vogue because there's this claim that you get predictability from the stratosphere back into the troposphere that is not accounted for by the ensemble spread. So the ensemble basically thinks it is worse than it really is. It's more predictable than the ensemble is suggesting. And that allegedly is coming from the stratosphere, which again has a different time scale than the troposphere. So do you think that any of this could be translated to this setup? That's my question.
I think that it can be translated, but regardless whether or not we didn't know that. But it's a very good suggestion. Actually, I'm not aware of this. Of course, in this model you cannot do it, but you can replicate. You can, of course, create mimicking model in which you artificially insert a time scale difference.
Yes, thank you. It was a very good talk, and I just wanted to add to the bibliography the work of Patrick Louraillot and co-workers. They ran a reanalysis. Reanalysis in strongly coupled way, and they have interesting results with that.
Yeah, can I follow up on that? I mean, of course, as I said at the beginning, there are many work, and this is a very important one. They do that by coupling via the outer loop, which is a very special thing that they have done. So I'm aware of that, but it's very difficult because I could not. So I have to say that this work by Penny and they have, it's a very good reviewer of that. But I'm aware of that. I'm aware of that work. We also had Patrick.
Okay, so let's thank you. Let's thank all the speakers of this afternoon, and so.